In this example, we're going to prove that the sum of all elements in row n of Pascal's triangle is equal to 2 to the power of n. Let's have a look at a part of Pascal's triangle. Let's say we choose row 3. If you add the elements in row 3, we have 1 plus 3 plus 3 plus 1, so that equals 8. And if we raise 2 to an index of 3, 2 to the power of 3 is also 8. Now, does that hold true for, say, row 4? 1 plus 4 plus 6 plus 4 plus 1 equals 16. But 2 to the power of 4 also equals 16. But does this pattern hold true for any row in Pascal's triangle? Let's find out. Now the question is, show that the sum of all elements in row n of Pascal's triangle is 2 to the power of n. Now the elements of row n of Pascal's triangle are NC0, NC1, NC2, so on, all the way to the end, NCn. Now let's consider the expansion of x plus y all to the power of n. So by the binomial theorem, x plus y all to the power of n is equal to nc0 x to the power of n plus nc1 times x to the power of n minus 1 y plus nc2 times x to the power of n minus 2 y squared plus ... and second last term, ncn minus 1 times x times y to the power of n minus 1 plus ncn times y to the power of n. Now if we let x equal 1 and y equal 1, clearly 1 plus 1 equals 2, 1 plus 1 to the power of n is equal to nc0 times 1, since 1 to the power of n is equal to 1, plus nc1 times 1. And if you go back to the expansion, 1 to the power of n minus 1 times 1, of course, equals 1, plus nc2 times 1, plus ... plus ncn times 1. So cleaning up the algebra and simplifying it, we have 2 to the power of n equals nc0 plus nc1 plus nc2 plus ... plus ncn, which is the sum of all elements in row n of Pascal's triangle as required. Here's another interesting example involving identities in Pascal's triangle. Show that n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. Now we know in Pascal's triangle, n choose r represents element r from row n. And we can get element r from row n by adding the two elements from the row above on either side of element r from row n. So that is row n minus 1, element r minus 1, and row n minus 1, element r. Here's Pascal's triangle. If we choose any particular element, it doesn't really matter which one, let's say we chose this element here, and this was n choose r, then these two elements on either side from the row above, this will be n minus 1 choose r minus 1, and this one here will be n minus 1 choose r. And of course, if we add those two together, we'll get n choose r. But the point of this example is to prove this identity, or to prove this, well, what we know is fact, but we need to prove it. So what we're going to do is we're going to start off by expressing the right-hand side using factorials. So this n minus 1 choose r minus 1 plus n minus 1 choose r, we're going to express these two combinations using factorials. So the right-hand side is equal to n minus 1 factorial over r minus 1 factorial multiplied by n minus 1 minus, now this is really important, you take note of this, r minus 1 in brackets, then close bracket again, so the outer bracket, factorial, plus n minus 1 factorial over r factorial outside of n minus 1 minus r factorial. Okay, so this n minus 1 is this n minus 1 here, and this r minus 1 is this r minus 1 here. So that will need to be enclosed in its own set of brackets. Now, of course, there'll be some cancellation in the next line. So that gives us n minus 1 factorial over r minus 1 factorial multiplied by n minus r factorial, since n minus 1 minus r plus 1, so if we expand the inner bracket here, we'll get n minus r factorial, plus n minus 1 factorial over r factorial outside of n minus r minus 1 factorial. So all I did there was just reverse the negative 1 and the negative 1 and the negative r around, so just swap them around. That way, it looks a little bit more familiar as to what we're about to do next. Now, we have a sort of a bit of a problem here. I'd like to have an r factorial in both denominators. So this r minus 1 factorial, somehow if I could find a way to turn it into r factorial, after all, our goal is to prove that the sum of these two terms is equal to n choose r, so we're going to need an r factorial. How do we somehow change r minus 1 factorial into r factorial? So r minus 1 factorial is just r minus 1 times r minus 2 times r minus 3 and so on. So if we just multiply this factorial by r, that's like multiplying the next term in the factorial. So that'll turn r minus 1 factorial into just r factorial, which is really nice, that's what we want. But if we multiply r minus 1 factorial by r, you need to do the same thing in the numerator, so to sort of compensate for that. And in the second fraction here, this n minus 1 factorial over r factorial outside of n minus r minus 1 factorial, it would be great if we can get just an n minus r factorial. But n minus r minus 1 factorial, it's like it's one element less. It's missing an element. It's missing the n minus r element. So if we multiply that back in, we can change n minus r minus 1 factorial into just n minus r factorial. So this n minus r minus 1 will just turn into this. Again, which is really nice. We'll have common denominators then. So let's multiply the denominator and the numerator by n minus r, of course. And n minus r minus 1 factorial multiplied by n minus r will just turn it into just n minus r factorial. So that gives rise to the next line. Once we sort of clean it up, we end up with r outside of n minus 1 factorial over r factorial n minus r factorial. And that's great because that's the denominator that we want. Plus n minus r outside of n minus 1 factorial over r factorial outside of n minus r factorial. So now we have two fractions with a common denominator. So naturally we'll add the two numerators together and see if we can get some cancellation or something that simplifies, and hopefully we'll end up with n factorial in the numerator. I'm just going to move these boards up. Just run out of board space. There we go. All right. So combining the numerators, okay, so we have r outside of n minus 1 factorial plus n minus r outside of n minus 1 factorial. We can factorize out the n minus 1 factorial. So factorize out this term here, n minus 1 factorial, and this one here, we end up with n minus 1 factorial outside of r plus n minus r. So this r and this n minus r will be in its own set of brackets there. And of course that'll be over r factorial, n minus r factorial. Actually, I'll just move the board so we can see the entirety of the second board there. Yep. Now r plus n minus r, of course the r's cancel. We just end up with n. So the numerator then becomes n minus 1 factorial multiplied by n over r factorial outside of n minus r factorial. Now, n minus 1 factorial multiplied by n is like the next term of the factorial. So that will turn n minus 1 factorial into just n factorial. So we end up with n factorial over r factorial outside of n minus r factorial, which of course is just NCR, which equals the left-hand side as required.